Hello, everybody. Hello. Welcome to the LIUniverse. I'm Dr. Charles Liu, and please call me Chuck. It is a great pleasure to be here today with my co-host, Allen Liu. Hey, Allen, how's it going?
Hi, it's going pretty well.
All right. Anything exciting going on at this very instant in the universe?
Yeah, Artemis splashdown happened pretty recently. That was pretty cool.
Ha ha!
Landed
Yes.
right in the Pacific there where it was supposed to, I think. So, good
The
stuff.
fact that it splashed down is like good. The fact that it splashed down because it was supposed to splash down is excellent.
Yeah,
Yeah,
a couple of spaceships have accidentally splashed down, but this one was on purpose.
Oh, terrific. And Artemis 2 is happening when, roughly?
2024, I think, is the current guess,
right.
but maybe 22 23, I don't know.
All right. Well, let's hope for the very best. And today's wonderful guest, I would love to welcome Dr. Aleksandra Kuznetsova. Hello. How are you doing?
Hey, I'm doing well.
It's terrific to have you. You are at the American Museum of Natural History, and you are a Sagan Postdoctoral Fellow, which, for those of you who don't know, is named after Carl Sagan. It's one of the prize postdoctoral fellowships that NASA gives to promising young scientists who are leading the charge in the research that we love to do about the universe. So thank you for being one of those wonderful scientists, Aleksandra. Can't wait to talk with you and chat about cool stuff today. Let's go right to today's joyfully cool cosmic thing. Or is it a joyfully cosmic cool thing, Allen?
It's a joyfully cool cosmic thing.
Okay.
I think you mix it around a lot.
All right, then. Joyfully cool cosmic thing today has to do with an exoplanetary system that has been researched for quite some time. It's called GJ3929. And it turned out that one planet seemed to exist around it, and it was an exo-Venus. But now researchers have shown that not only is there an exo-Venus going around it, there's also a mini-Neptune. Okay, so that is a weird solar system. Aleksandra, what the heck is an exo-Venus and what the heck is a mini-Neptune?
Well, all my planets are fake, so
we'll get to that.
They live in a computer, but generally, exo-Venuses and mini-Neptunes are ways we like to characterize planets outside of our own solar system. We like to compare them to solar system analogs because as a solar system, I guess we're pretty self-centered.
Yeah.
Well, we know the planets here are the best, I think.
No, of course. We don't call Venus like endo-Venus. Maybe we should. That. Yeah.
Endo-Venus. We're on an endo-Earth, you know?
Yeah, we are on endo-Earth as opposed to an exo-Earth or something like that. But yeah, this exo-Venus around GJ3929 has an orbit of only a couple of days. And the mini-Neptune, it has an orbit of only like 2 weeks. So this is a very, very compact system. And we think of Neptune as this cold, distant planet that's like, billions of miles away from our sun, and the temperatures are hundreds of degrees below zero, right? So what is a mini-Neptune doing on such a tight orbit? Aleksandra, do your fake planets actually do that?
Well, it turns out most people's fake planets do that because of there's quite a conundrum usually referred to in planet formation. So when you make a planet, you want to make it, and if you make it really quickly and it becomes really big, then it can actually start migrating through the disk of material that it's being born out of. And if you don't stop it, you can actually get it, gets chucked into the star.
No!
So a lot of planet formation is actually how to keep your planets once you've made them. And so it's not super surprising. I think it's pretty common that people think that migration is one of the leading channels, they think, for pretty close in fairly large planets like that.
That is so interesting. How long does it take for a planet like Neptune to migrate from billions of miles away from the sun down into like a 2-week orbit?
It depends. On whose model you ask, but on planet formation timescales, i.e., like usually we're sort of thinking about planet formation occurring over 1 to a few tens of million years, it is definitely very achievable on million-year timescales, most definitely. Even shorter timescales, even, depending on what fancy angular momentum you're using.
Okay.
Really shove the planet inward.
Yeah. So how do your fake planets? So you say you simulate planets on computers. I mean, that sounds pretty cool. It sounds like it could cover a lot of different kinds of things. So how do you specifically do that, and how to relate to other people doing this?
Yeah. So I guess to be more accurate, I simulate how the ingredients of planets move around in a big old, what we call a protoplanetary disk. This is sort of, you can think of it as a big pancake full of gas and interstellar dust, and it's swirling around a star that's being born in the center. And essentially everything you need to make a solar system is already in the kind of interstellar clouds that we see. So the disk just has, micron-sized grains at the start, we think. So, 1/10,000th of a centimeter. And somehow we have to sort of shove them all together into a close enough space to make big rocks. So a lot of planet formation is kind of centered around this question of how do we collect enough stuff to make the planets? And then how do we collect it in the locations that we think planets are being born? And then how do we bookkeep what they're made of?
All right, so Alan, I think it's time to ask Aleksandra a student, or more accurately, have a student ask Aleksandra a question.
Yeah, all right. So this question comes from a student named Kevin, and Kevin is asking, how could you create an artificial magnetic field for a planet like Mars?
Interesting. I assume this question is because Mars does not have a magnetic field, and it used to have one.
Yeah, that's probably the idea. Yeah.
And I guess for context, then, we think that Mars had a magnetic field, and we think that the magnetic field actually helped protect the atmosphere from irradiation from the sun, and so it's actually pretty nice to have a magnetic field because it makes things kind of homey, like we have here on Earth. And after a while, Mars's internal dynamo, the thing that generates a magnetic field, shuts off. Mars loses the atmosphere, and now it's kind of cold and hard to breathe down there.
Fair.
But as far as what do you need to make a dynamo for an entire planet, I don't know how you would build one, because generally you need a bunch of, if you're going to go with primary dynamo theory, what you really need is a bunch of molten metal material that is conductive, and you need it to be rotating.
Wow.
So you need a bunch of liquid metal inside the center of your planet.
Holy moly. So we do have such a thing in the center of Earth, right, Aleksandra? That's why we have a magnetic field?
Yep. Earth has a dynamo inside, a geodynamo, and that is what helps us not get pummeled by high-energy particles from the sun, generally.
That's really cool. Now, what would happen? So actually, what would happen if our core stopped spinning is that we would lose our magnetic field, right?
Yeah.
Yeah, but how realistic is that going to be happening? In fact, I remember some disaster movie from the 1990s or something where actually that happened and humans had to go down there and restart the spinning of the core. Do you remember this?
Yes, I think, yes, that was a thing.
And I think the movie was called The Core, right?
Yes, it was called The Core.
I didn't see it though. Alan, you probably didn't see it because I
haven't seen it.
Born when it came out. Maybe
I might have been.
You might
have been, but I might have been real small. But
Alexandra,
I've heard it's only okay, or maybe not even that.
Alexandra, did you see it?
I did. I don't remember everything that happened. I remember being quite disappointed because I went in thinking there would be a lot of, core. But that was a relatively small part of the movie, and I was pretty sad because they didn't spend a lot of time on the actual core bit.
That's too...
Yeah. So in the movie they're trying to restart Earth's core to have a magnetic field going. In real life, I mean, first off, we don't even know how to get to the core. But besides that, if we were going to do that on Mars, that would take a whole lot of energy, right?
Well, the thing is, Mars is already spinning. I think with
Okay.
Mars, the problem is, in fact, that the core is just too cold, and
Oh,
it does not slosh about in the right manner.
okay. So is there something else we could do? Could we like put like a bunch of neodymium magnets at like its orbit or something, like without even do anything? Is there that much neodymium in the solar system?
I don't know. Sorry, I'm trying not to embarrass myself because I did paleomagnetism in undergrad.
Oh,
Oh,
really?
awesome.
So, yes, you're right in that ferromagnetic materials like neodymium have a magnetic field. I don't know how much neodymium you would need to generate the type of magnetic field that would actually be able to
Like do anything for Mars?
do anything on Mars. Yeah.
Yeah.
Well,
okay.
I
the
think
magnetic,
a relatively inefficient way of magnetizing.
Yeah, it sounds like it could be.
Right. It's quite a lot of energy involved just to heat stuff. Or in the case if in the core like movie, right, you would have to speed it back up again and start it. But the amount of energy, I don't think people realize just how much kinetic energy there is in the Earth's spinning. Like if you just take the Earth's core, maybe 1,000 miles across or something like that, and you imagine it spins around once every 24 hours, the amount of mass in there, your result is like way more than a million atomic bombs or something, right? I mean, just like so much energy.
Probably even more than that. Yeah.
Oh yeah, billions. I don't know. Who knows?
I'm just thinking, right? Because like part of the reason like we can get tidal energy, like from like tidal power plants and stuff like that, is because Earth's spinning is interacting with the gravity of the moon, and so if like we can get that energy and use it to power the power grid, and it does like basically nothing noticeable to Earth's spin, then I presume that just means there must be tons and tons and tons of energy in the Earth's spin, and we're not doing anything to it.
Without doubt, right? And that energy is being bled off in the tides, as you said, and it's caused the moon over billions of years to be facing us on one side all the time, right? So presumably something like that can happen over time too in that system. Now, Aleksandra, when you are thinking about the creation of entire solar systems, you're thinking about things like this, right? Magnetic fields being formed, the rotation of things, and this thing you were describing earlier about a solar system, a baby solar system with a star just barely igniting on the inside. It's still embedded deeply in a cloud of interstellar material, right? How does that affect the formation of planets like the Earth?
Well, I'm glad you asked because this is my favorite topic.
Nice.
No, not a planet at all or anything. So it's quite interesting because when we talk about this phase of, planet formation, we generally call this part of the disk the embedded phase. And for a really long time, it was kind of like we don't talk about the embedded phase because it's quite inconvenient. Because observationally, if you are within a big old cloud of material that's very dusty, it's super hard to see through. Unless you have kind of infrared wavelengths and
James Webb Space
JWST that, but we really haven't had IR observations since Spitzer. So it's been a real sad part for and with embedded systems, like you really need to be able to see past the cloud of material, and it's really even hard in the millimeter, like with ALMA or NGVLA, because it is just there's a lot of stuff in the way, and you really can't tell what's going on inside.
I see. Now
done
ALMA is the Atacama Large Millimeter Array, right? And NGVLA is the Next Generation Very Large Array. That's in Arizona. Oh no, New Mexico, right? Those could see through them if you gave them a time or something?
Yeah, so there have been actually a lot of neat studies with ALMA as of late, in which people have spent a lot of time and very careful analysis actually trying to get at where the part of the disk is inside these embedded systems and trying to kind of probe, like, hey, can we separate out what is in this big old cloud in front and what's rotating in the disk inside? And because ALMA allows you to generate maps of molecules, which with pretty much unprecedented resolution.
That's pretty cool.
Great. And because with gas observations and in in the radio, you can make these things called channel maps, which
Mm.
actually allow you to see how much of stuff is moving at different velocities or different
Oh.
speeds. And so you can start, if you have a nice model, to try to separate out material based on how it's moving.
Wow. So what's the bottom line of the embedded phase? Like, is stuff going on in there actually that, say, for example, utterly upends all our regular neat ideas of how planets form? Or is it just
I would
like,
really like for people to believe that. This is my
oh,
traveling, carnival salesman pitch. Did you know
yeah.
that if we actually simulate the embedded phase with, numerical simulations
Mhm.
instead of, well, we spent a lot of time in the 80s doing pen and paper models. And so when you're
Okay.
doing pen and paper, everything ends up being a sphere and everything ends up being very symmetrical.
Mm.
And
Yeah.
star formation is just not actually that spherical. Things are pretty messy, lots of gases flying about. And so when you actually have sort of a more realistic setup where you can account for the messiness, where you allow kind of big old streams of stuff to fall onto the disk rather than just sort of a little quiet spherical collapse, you can essentially shake things up a lot.
Oh, okay.
And so when you start doing things, so you can imagine there are these very large, long, what we call like filaments or streamers,
Mhm.
and they're impacting the disk because the disk has its own gravity and its own rotation. And when they hit the disk, they actually, impart a lot of momentum and energy and all fun things that we like to keep track of in numerical simulation. And the disk feels it and it responds, and it actually changes how material in the disk itself moves.
Oh, wow. So that means that the planetary formation process itself is heavily affected by all these streamers and all the stuff coming in.
One of the interesting things we've learned that essentially when you shake things up a bit, you can make the medium in the disk more turbulent, and so things can fly around a little faster. And it turns out that's actually kind of good if you want a bunch of dust to stick together because you need it to glide.
Oh,
It
Get
is
little bits
also
of
good,
dust to turn into
and
big
it's
chunks.
also good for solving some of the problems we talked about earlier, where if we've made larger pieces of rock, how do we not lose them into the big star? Well, what we really need to do is put up some sort of barrier, something that stops it from drifting inward. And turns out when you smack a bunch of stuff into a disk, you actually increase the pressure in certain locations. It acts like a little fence and sort of starts collecting your rocky dust and planet-forming material into things like rings, but it also means that it stops it from going further in.
Well, that's great.
So theory for me, because I think that it's very self-consistent, we can tell a story that's works well with our idea of what's going on in star-forming environments.
Right.
And you can make your planets and keep them too, which is
that's good. Yeah, we don't want all the planets crashing into the star.
Yeah, that's no fun. That's great. Do we have another question? Do we have a question for Aleksandra? Let's bring in another question.
We do have a question. This question is from one of our patrons on Patreon.
Cool.
Which is awesome. If you want to, everyone listening, if you want to join us on Patreon, you can get your questions answered. Patreon questions get some priority here. This is actually sort of going back to some of the stuff we were talking about before about, narrative building and stuff like that. The question from Cameron is, Carl Sagan said, "We are a way for the universe to know itself. But is there a stigma that makes this knowledge unattractive to people? How do we inspire more people to learn more?" And so I think part of the reason we're asking this with the Sagan quote to you specifically is because you're a Sagan fellow. So a little bit of a connection there.
It's interesting to me because I'm not sure there is really a social stigma to saying stuff, right? Like, I don't think that's necessarily true. I do think that, especially with astronomy, sometimes there's a disconnect between kind of like how professional astronomers interact with the public and the standards and norms of their profession and kind of how we draw people into astronomy. Like, Carl Sagan is a master, obviously, of the things that he does. Like, even as a professional, like, I would be reading, like, Cosmos and tearing up a little because I'm like, wow, Carl, it's, like, really beautiful,
Yeah.
And a lot of the things that make Cosmos feel so profound is that, in a way, the book is kind of art. It's making you feel something he's telling you stories and he's evoking emotion, and it's really kind of a thing that we most associate with art. And in the 21st century, we like our disciplinary boundaries a lot, and we tend to be like, hey, science is objective, which is not, and then art is this other thing, right? But as we talked about it, like, everything we're doing is also, it's storytelling, it's a human enterprise. Like, it is inherently kind of not going to be just cold, hard facts, as you said. And what strikes me kind of about that Carl Sagan quote is like, we are a way for the universe to know itself, is when I think about it like every person is a unique combination of things and experiences and perspectives. And in a way, like, that's kind of what matters in that sentence. Like, and I think Carl touched a lot of people because he made people feel like they matter, right? Like, you are connected to the cosmos. So that's really kind of, that is the feeling that people are looking for a lot of times. And sometimes when we are like, oh, I am, only here to look at the telescope and read the pixels, I cannot comment on the metaphysical implications of, cosmology, which I can't from a professional standpoint, obviously. But I think that sometimes we lose a way to actually talk to each other about the things that inspire awe and wonder.
Yeah. So let's just all pretend that we're experts at metaphysics and think about things even though we don't know what we're talking about because it's cool and it makes us feel good. What do you think of that?
I don't know if it's even just that. Yeah.
I personally don't enjoy metaphysics that much, but I think that a lot of people who come to outreach events definitely do. But I think there's a way we can be inspired by the ways in which people in the past have kind of interfaced with scientific knowledge and art. I think my favorite example nowadays, I actually use it in my scientific talks to throw people, is Vasily Kandinsky, was a painter.
Composition 9 is one of my favorite non-representational paintings. It lives in the Guggenheim most of the time.
Or is that one 8?
Oh, Composition 8. Composition 8 is my favorite one. Composition 9 is a different one. Composition
also
8.
Cool. They're both cool.
Vasily Kandinsky's Composition 8 is my favorite piece of non-representational art. It hangs in the Guggenheim when it's not traveling around the world. So tell me, you got to tell me about Kandinsky and how you're doing this. This is fantastic.
I like to talk about Kandinsky because, he was the early, 20th century. He was in the Bauhaus movement. He was doing all these things with shape and form, and his art is really geometric. And one of the other things that you kind of learn about him if you read about him is that he was also just like a giant nerd. By those standards. He was really into the natural sciences. Like, he kept up with new discoveries. He was very much intrigued by kind of what it all means and how he can fit it into his own kind of art and storytelling. But he didn't view it as sort of separate, right? He was incorporating it as this sort of like fundamental understanding of the human experience. There's one painting that he has that is in these like pale pink hues.
Okay.
And it's inspired actually by early microscopy images. And
wow.
Called capricious forms, which I think is just a very affectionate way of thinking about microorganisms.
That's fantastic.
And so I really kind of like that, not being afraid to sort of bridge how one, the vibes, what gets. Bring the things one learns.
I think that's great. Capricious forms. That's wonderful. So, Alan, I bored you, hopefully didn't bore you. I know that I regaled you over and over again with Composition 8 when you were a kid, and your siblings as well. Yeah, and in one corner, there is a black circle within which there is a red circle. And I remember always wondering, like, maybe that's a black hole or something, a non-representational way of saying it, or maybe like a record or something like that. But now, Alexandra, you're telling me that Vasily Kandinsky could very well have thought of that as a scientific, artistic, emotional, amazing thing. That's even cooler to me.
Yeah, no. So I became kind of obsessed with him because the Guggenheim is like exhibit around the swirling ramp with
Wow.
his development through time. And then I was in Paris for a conference. And I stopped into a used bookstore and I just like found this book that was written by Kandinsky, and it's called "Concerning the Spiritual in Art," in which he refers to the spiritual as basically vibes, kind of. And he has all these chapters about how to make shapes tell you what you're feeling. He has complicated diagrams. He assigns emotions to every color. It's pretty.
Wow.
He is in fact a giant nerd. But so there are lovely chapters called "The Movement of the Triangle."
Wow.
Sounds almost like Johannes Kepler back when he was talking about the harmony of the Harmonia Mundi, talking about the music of the sphere. Is there a quote in there that's really cool? What does he say? Like, show me one quote, or he quotes one person that's like something particularly cool.
So it says, "What is the message of the competent artist? To send light into the darkness of men's hearts, such is the duty of the artist," said Schumann. So he really does think that artists are supposed to make you feel stuff about the world.
There you go.
Definitely not whimsical, capricious forms, huh? You have a solemn duty if you're an artist. You gotta bring the light into people. Wow.
If you can make somebody feel affection for microscopic organisms, I think that's also an accomplishment.
Yeah.
Well said. Well said, Alexandra. Whew. We have gone through so much, and yet I feel like we've just barely scratched the surface. I mean, I want to talk about like bad movies or B movies, which aren't bad, right? You like them. I want to talk about like crazy stuff. I want to talk about, I don't know. Okay, before we wrap up, Alexandra, just tell us like one movie that you've recently seen that you really like, and just riff on it. I mean, I just want to hear about it.
I will always hype up Everything Everywhere All at Once because that's my favorite movie of the past year.
Yes.
I've pretty much bothered everyone I know to go see.
Absolutely. Michelle Yeoh, of course, is magical, has always been. Just amazing actor. But then the guy who played Short Round in Indiana Jones and the Temple of Doom is now an adult in this movie, and there's yes, we shouldn't spoil the characters. Are just funny, and the whole thing. I mean, in a sense, Everything Everywhere All at Once is almost like a cosmic video game, right? You gotta power up, you gotta do this, you gotta go back and forth, and then there's this interaction between young people and older people and generational things and families who care about each other but don't know how to talk about it. And I mean, there's just all kinds of. I'm so glad you like that movie because I love that movie too.
No, I love Michelle Yeoh. I want her to get everything good in life. That movie was so delightful, and I just remember like just constantly being sort of thrown between laughing and crying, and it was one of those things that like you were really having the feelings while you were watching it. It was excellent.
Alan, you saw this movie, right?
I did, yeah. I really enjoyed it myself too, yeah.
Mm-hmm. And 100% with you on the laughing then crying was just amazing. Dr. Aleksandra Kuznetsova, I wish we could go on and on and on, but we just have to wrap up for now. Will you come back? Will you do this again? Can we chat some more in the future? Please, 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 please.
Sure.
Thank you. Can't wait to talk about all these wonderful things. So, how can we find out about your work? Can we find you on social media, or can we find you on some other way, media things, books, whatever, that we can find you?
Well, there's my website, which will be astro.kuznetsova.com, which is my last name. And I guess there's Twitter, but I don't really tweet much.
Fair.
I'm
That's
mostly
okay.
use it, read about what other people are doing. That's at 1AU away, the number 1, and then AU, astronomical unit, away.
Wow, that's cool.
I love that. That's a great Twitter handle. Congratulations.
Thank you. I
That was
felt
smart.
very clever when I came up with it.
Nice.
Make sure to tweet some more so that I can use that, okay? Or put it on Mastodon or something so that we can see it in more than one place. 1AU away. I like that. Thank you. Aleksandra, it's a pleasure. It's really, really great to have you. Thank you very, very much for being with us today.
Yeah, thanks for having me.
Allen, as always, thank you so much for being an awesome co-host. Is there anything else you want to say before we head on out and call it a day?
I don't know. I'm just glad to have these kinds of conversations. It's always really exciting to see what everyone thinks about these kinds of things.
Terrific. Thank you, Allen. And to all of you in the audience, thank you for being with us today. Thank you. If you like what you hear and see, please find us on Patreon. Support us. We'll do more of this wonderful stuff and hope to get you as much as you would like to enjoy about all the things that we talk about here on this show. So thank you for being here with us today. Thank you for being a part of the LIUniverse.